Hello everyone. This video is also going to be slightly long, but again we're going over the periodic trends, which encompass a lot of different things in them, but I'm hoping that I can explain things and hopefully make a little bit more sense, and then hopefully you guys can get some practice in, right? So these next two are, in my opinion, two of like the harder ones to understand, and the only reason why I say that they're two of the harder ones to understand is mainly because they have a lot of exceptions, right? So we're going to go over some of those exceptions, and some of the other exceptions just don't make any sense. It's a little funky, right? Especially electron affinity. That one, it just gets a little crazy. But we'll go over some tips and tricks to kind of help you out, right? So the first periodic trend I want to talk about in this video is ionization energy. So what ionization energy is that it's the energy required to remove an electron, right? So it's the energy required to physically remove an electron from an atom. In general, we say that the larger the atom that it is, it's easier to remove an electron. There are some exceptions, which we'll go over, but in general, the larger the atom, the less energy, or the easier that it is to remove it, right? And that makes sense, when you're thinking about it like a magnet, as we can think of it, you have the positive things in the middle and the negative things on the outside. The further away the things are, the negative things are from the positive things, the less likely the positive things are going to influence the negative things, and therefore it's easy to just kind of like pick off an electron. How I like to think of it, like the nucleus gets angry. Like that's the energy required to remove it. It's like, ugh, give me these electrons. I want to keep them. So it has less of a hold on those outer shell electrons when it's larger, right? Versus when it's smaller, the electrons are really close to that nucleus. Therefore, it's going to require a lot more energy to pluck off an electron. So I have the general trend here where purple is showing where the ionization energy is increasing. So as you move along, you're going to be adding or getting increasing ionization energy, and that's due to more protons, so the electrons are closer. And then as you move up, the ionization energy also increases because you're removing energy levels as you go up, meaning that the atom becomes smaller. So I also have written here that energy is in joules. So if you look at a chart, it might say like kilojoules, megajoules, whatever. Energy is always in joules, so that's what you'll commonly see. So down here, I have an example where actually the largest and the smallest atom present on the periodic table. So the larger the atom, it has the lower ionization energy. So francium has the lowest ionization energy. It's really easy to take an electron off of francium. It's barely even holding on to those electrons at this point. And then helium is really, really tiny. So tiny. It does not want to get rid of those electrons, so it takes a lot of energy to remove those electrons, meaning it has the highest ionization energy. So I want to really quickly go into the differences in ionization energies, and then I'll also go into the exceptions, right? So there's a first ionization energy, a second ionization energy, and a third ionization energy. So the first ionization energy is the energy required to remove the first outermost electron. So it's that first electron that we're removing, right? And then the second ionization energy is the energy to remove the second outermost electron, right? So these are labeled IE1, IE2, IE3, and so on and so forth, right? So it's basically just the amount of energy to remove each electron. So you can kind of think of it like picking berries off of a bush. You remove one berry, you remove a second, a third, a fourth, a fifth. Eventually that bush is going to become bare. There's not going to be anything on it. But like that's kind of what it is. You kind of work your way in. Whatever. And as electrons are removed, the atom becomes smaller, and therefore, as the electrons are removed, the ionization energy goes up, right? So the first ionization energy is always going to be less than the second ionization energy. And we can think of it like this, right? Atom, say, We remove this electron. Oh, bye-bye, electron, you're leaving. So we're going to actually end up getting rid of this whole shell here, saying bye to all this. And all we're left with is this, meaning that the element has gotten smaller. So when we remove that electron, and so on and so forth, it gets smaller and smaller and smaller and smaller, meaning that based on the general trend, the ionization energy will go up. Okay, next thing to talk about is the exceptions of this. So this is where it can kind of get confusing. Same thing as I say with any videos, like if you're confused while watching this video, I do highly recommend you viewing other people. Again, I'm not a professional, I'm just going over the things that we went over in class to help out my classmates and also to help myself out. So I'm no professional. I am trying my best, but if this is not, if you're stuck on this, check out another video, talk to Professor Sherlock. He's great, one-on-one office hours, he's very helpful. So yeah, definitely think about doing that if you are a little lost here, but I'm going to do my best. So electrons require more energy. So this is going to go along, just as an FYI, this is going to go along with both electron affinity and ionization energy, so keep this in mind as we do like all of these. So yeah, alright, so electrons require more energy to be added or removed to a more stable atom. So the more stable an atom is, it requires more energy to remove those electrons, right? Because they're happy. Like, they don't want any more electrons. They don't want their electrons to be removed. So they're like, no, don't give me more electrons. And if you're going to give me more electrons, I'm going to release a ton of energy, absorb a ton of energy, etc. And things like that. So let's look at some examples of when atoms are more stable based on their electron spin and their orbitals, right? So the first one, here we have a p group. So this is something p3. So 1p3 doesn't exist. 2p3, 3p3, 4p3, right? The ending of the electron configuration, which I have a video on electron configurations if you're a little bit confused about that. And orbital notation as well. So here is that orbital notation, right? So we have spin up, spin up, spin up. This is when they are the most stable in this orbital. Obviously, they're most stable when they're all the way down and they have a happy octet. But before then, they are very stable here. So it's most stable when all of the spins go the same way, which means that it's harder to remove or add these electrons. Looking at a S group, so this is S2, something S2, 1s2, 2s2, 3s2, whatever. It's a very stable S group. So because it's completely filled, the more, if you have a filled subshell or a filled orbital, that means that they're not going to want to get any more electrons, right? So when you are adding electrons to this means a whole new orbital has to be made, right? So this atom has to spend a lot of energy just making a whole new orbital. It's kind of like, drawing out our orbitals. We're like, ugh, I have to draw another one now. Like, that's a pain. That's exactly how the atoms feel. So they're like, ew, don't want to add this. So that means that the ionization, or the electron affinity, right? So this is me skipping ahead a little bit, but the electron affinity, in order to add an electron, it's going to require more energy because you have to add on that orbital. But this is just something to keep in mind as we go through those little exceptions there. So I'm going to do an example of the ionization energy. So first question is, which will have a higher ionization energy? First question says sodium or rubidium. Oops. Okay, there's my periodic table. So we have sodium and we have rubidium. So sodium is smaller than rubidium, and that means that rubidium is bigger. So that means that it would have a lower ionization energy. So to have a higher ionization, let me just add a note here. A higher ionization energy means harder to remove electrons. Harder to remove electrons. So sodium is harder to remove the electrons because rubidium is larger. So I'm going to write this larger. Alright, so then we have carbon and fluorine. So carbon and fluorine are on the same energy level. So in order to do the atomic radius, we have to look at their protons. So carbon is going to be slightly larger than fluorine because fluorine has 9 protons and carbon has 6 protons. So carbon's going to be larger, meaning that fluorine is going to have a higher ionization energy because it's smaller. So now let's get into some practice problems for ionization energy. So same thing, circle which one will have a higher ionization energy. All right, so fluorine and I think that's bromine. Fluorine and bromine. So we're looking at the energy levels here of which one's bigger. Fluorine has 2 energy levels and bromine has 4. So bromine's going to be bigger, meaning that fluorine is going to have a higher energy level. Now we have sodium and strontium. Same thing, strontium is higher in energy level, so it's going to be larger, meaning that sodium is going to have a higher ionization energy. All right, carbon and fluorine, we just did that. Oh, did we do carbon and oxygen? All right, well, we're doing carbon and fluorine. Fluorine's smaller, so that means that it's going to have a higher ionization energy, so that will be our answer. And then we're going to do krypton and potassium. So krypton is a noble gas, so I'm going to assume that this one's going to have a pretty, like a decently high ionization energy. Let's see. So potassium is a lot bigger than krypton, so I'm going to say that potassium has the lower ionization energy because it's larger. Due to the number of protons that both of them have. So I'm going to say krypton here is going to be our higher ionization energy. And then the challenge is nitrogen or oxygen. All right, so nitrogen or oxygen. So here we're looking at what's going to require more energy to remove an electron. All right, so I'm going to actually look at their orbitals here. So, because I can tell that this group here, this is where like the problems kind of start, is in this little section. So nitrogen's S group is gonna look like, I think it's all happy one. So that one's happy, 1, 2, 3. Yep, that one's happy. Oxygen is gonna look like that. I'm gonna say that nitrogen is gonna be higher because it's already stable. So that means in order to remove the electron, like I feel like this one's gonna be fairly happy to remove the electron because that'll make it more stable. So it's gonna require less energy. So we're gonna say that this one's higher because this one's already stable. I'm gonna check my answers really quickly with this little graphic here. So yeah, nitrogen would be higher. Krypton, much higher than fluorine is higher than, yep. And then sodium and strontium is interesting. So they have strontium higher. Actually, no, they look about even due to this graphic. I'm gonna see if maybe there's on here. Ionization energy. Let's see if they have a little graphic for it. Ionization, okay. So they're about the same, but I think on a test, due to the energy levels, I would say that sodium has the higher ionization energy. Yeah, that's what I personally would say. There's probably a chart out there that can confirm that, but then we're looking at FNBR. Let's look at this. FNBR. Where's BR? Oh, BR. Yeah, F is going to be higher. Okay, cool. Alrighty. So let's move on to electron affinity. So electron affinity is one that, again, I like to say it's crazy. There is so many things going on in electron affinity. It is actually insane. But again, I'm going to try my best to help you out here. So electron affinity is the energy released or absorbed when an electron is added. So an electron is added to an atom, right? So affinity is attraction. So it's basically like how much a atom would become more stable if an electron was added. So it's kind of like, the smaller that an electron is, or the smaller an atom is, the more likely it is to attract electrons because it wants more electrons, right? So if you think of something like chlorine, oops, that's not a pen. So if you look at something like chlorine, all it needs is one more electron in order to get to its happy octet. So it's going to have a high electron affinity because it is attracting electrons. Like, it loves electrons. I like to think of it as of electron love because that's also what affinity means. It's like a love or attraction for something. But that's what I think of it as. But yeah, so that's one way to think of it, right? So when something's endothermic, it means it wants to gain those electrons, right? So that would be represented by a positive delta H because it's endothermic. And then for exothermic, as a delta H that is negative, that means it doesn't want to gain the electron. So when we look at a noble gases are already stable. So they're like, no, I don't want an electron. Please don't give that to me. So when you add an electron, it's going to have a exothermic reaction because it doesn't want to gain those electrons. So I have written here also that generally as atomic radius goes down, the electron affinity goes up. So same thing with like the periodic trend, right? So as you move across, the electron affinity is going to go up, and as you move up, the electron affinity is also going to go up. But again, there is exceptions to this when the orbitals are added or they're in the same spin, right? So here's a graphic that I actually pulled right out of the textbook. So we can see here that when the spin is up, all it needs is one more, or this is like an S group, right? So let me write this. This is S, this is S, this is a P, this is a P. So this is an S sublevel. So in an S sublevel, when there is one electron in there, it's going to look like this. It's going to be one up, right? And if I were to add an electron, it would look like this, which makes it more stable. So this is really easy add for them, right? When we look over here in an S group, when there's two electrons, that means that the next one you have to add is going to be in a P group. So that's going to require a lot of energy for it to do, which means it's not easy for it to do, which I talked about a few slides ago. So that means that it's going to be it's going to have a smaller electron affinity. And then here in a P group we're going to look at, in order to become stable, as I said before, it wants to be up, up, up. That's what makes it the most stable. So adding an electron here is going to be really easy. So the electron affinity is going to be up, right? And then down here, same thing as I talked about before. Again, it's up, up, up. It's already stable. It's not going to want to add those electrons. So if we put one here, it's not going to be happy. So it's going to be less easy, meaning that the electron affinity is going to be down, or exothermic, or 0, or close to 0, or something like that, right? It's going to be lower. So now to move on to some helpful things to know about electron affinity. So these are things that I like to memorize. So that helps me kind of keep track of all these exceptions when it comes to electron affinity, right? So the first is always going to be, or the first highest electron affinity is always going to be group 17. The reason why is because group 17 here, this is group 17, they only need one electron to be 100% stable. Not even stable within orbitals, stable as an atom, right? It's going to have that happy 8 octet. So gaining an electron is very ideal for it. So it's going to exert a lot of energy. Like, for me, an exothermic reaction, I like to think of it as like things being happy. They're finally stable. They're like, heck yeah, I'm so happy about this. I'm stable. This is awesome. So these guys are going to be the most happy when an electron is added. And then the second lowest group, so the most unhappy group, is the noble gases. And that's really just because they are already happy. They don't need anything else. They're chilling. They don't care. They, like, literally, they don't care at all. They're like, add an electron and see what happens. You know, like, they're happy where they are. They don't want an electron. They don't want an electron removed. Everything like that. And the second lowest is group 2, which is the alkaline earth metals. And I said an exception with nitrogen because if you look here in this graphic, nitrogen's like an oddball here where it's negative, just because it's so small and because of the fact that it has that happy D group or that happy P group already, so it's gonna, you know, be endothermic. But yeah. So the second lowest is group 2, and that's the alkaline earth metals, right? And that's just because it has to add on an energy level in order to add an electron. So it takes a lot of work for it. So it's not really happy with that situation, and we can see that here where they're either going to be 0 or really close to 0 because they have to exert energy to make a new sublevel. Okay, so let's do some electron affinity examples. So which one would have a higher electron affinity? So we have neon, oxygen, and fluorine. So neon, we can already say that one's not going to be a high electron affinity because it's 0. It's always going to be the lowest. And we have oxygen and fluorine. So oxygen is slightly bigger than fluorine. So that means that when you add on an electron, it's not going to be as happy as fluorine would be because fluorine is really small and it's really close to its octet. We can also say that because fluorine is in this halogen group that it's going to be the highest. So we can cross this out and fluorine's going to be the highest. Now we have sodium, rubidium, and cesium. Sodium, rubidium, and cesium. So I can say right now that cesium and rubidium are much bigger than sodium because you have those 2 extra energy levels. So I'm just going to cross these guys out because they're massive compared to sodium, and I'm just going to circle sodium. And then let's confirm that with this, right? So we have fluorine is the highest, and yeah, that's definitely true. And then sodium, rubidium. So sodium, rubidium, and cesium. Sodium has the highest, so cool. Very awesome. Alrighty, so the last thing, where'd it go? There we go. Last thing is some electron affinity practice problems. So same thing, which one would have the higher energy or electron affinity? So if you want to pause the video and try it out yourself, go for it. If not, I'm going to go through all of these now. So we have, let me find my periodic table. So we have lithium, sodium, and potassium. Lithium, sodium, and potassium. Okay, well this one's kind of simple. Lithium is the smallest, so I'm going to circle lithium. I'm going to check my answer with these ones because these ones are a bit wonky. Okay, so we seem good there. Lithium is the highest. And then we have chlorine, bromine, and iodine. So chlorine, bromine, and iodine. Also pretty simple. Chlorine's going to be the lowest because it's the smallest. Let me just check that. Chlorine, bromine, and iodine. Alrighty, yep, that one's the highest of those. And then we have boron, carbon, and nitrogen. So I'm going to already cross off nitrogen because I know nitrogen's negative just because I have that memorized. And then we're going to look at boron and carbon. So I want to say that carbon, alright, well, let me think. So boron is slightly bigger than carbon. So I'm going to say that higher electron. Okay, so I'm going to say that carbon is going to be higher, but I want to check that because that region does get a little wonky. Carbon, did I say carbon would be higher? Cool. Got that right. Let's go. Alright, so then we have radon, helium, and neon. Oh, this one's kind of a tough one because these all are noble gases. So we're going to have to look at their atomic radius. So we have radon, which is the largest, so I'm going to already cross that guy out. Helium, which is the smallest, so I'm going to assume that it's going to be helium, so let me underline that, and then neon. So I'm going to say that helium is going to have the highest electron affinity because it's the smallest, but let me just check. Yeah, it's 0. So, oh, yeah, the highest. Okay, yeah, because these are negative. I'm like, numbers. No, okay, we're good. So yeah, helium has the highest electron affinity. Alright, so thank you all for watching this video. Again, feel free to practice. Again, I am going to be posting those practice problem sheets that I have for you guys to try out yourself in the description box below. So thank you all for watching, and have a good one.